All right, our second speaker is Robert Bajons. Robert is a final year PhD student in statistics at the Vienna University of Economics and Business. He is mainly interested in statistical models for all kinds of team sports containing some form of a ball or puck. Fun fact, he is also currently the second all-time leading scorer in his amateur soccer team in Vienna, 125 goals and 180 appearances. You have video stream. Oh, it's on this. Okay. So if you put this on and then you click.
Okay, so I hope you can hear me now. All right, great. Thanks for the introduction. Yeah, I'm happy to be here again at NESSIS. I'm going to talk about player evaluation today, and this is a joint work project with my colleague Lucas from WU Vienna. And just as a quick side note before starting, so if you want to follow along with the slides or get more information, you can try to scan this QR code. You'll find it on every slide. Okay? So how do we commonly evaluate players in sports? Well, I think there's more than one good answer to this question, right? But recently there has been one particular approach that has been very popular, and it involves estimating expected values. Okay, so what you would do with this kind of expected value metrics, you would compare an actual outcome to some expected outcome that you estimate from a model. Okay, so you need to kind of find a good way to estimate the outcome depending on some covariates that you have. In soccer, this could be, for example, an expected goals model or something like that. And then what you would do is you take all of the outcomes of a player that you're interested in, and then you simply look at the differences between this actual outcome that is observed in the data and the one that you expect. Okay? And there's a number of examples. So in soccer, we would call this goals above expectations, or GAGs for short. And ice hockey, I believe you use the same term. In basketball, you maybe call this quantified shoot impact or something like that. And then you have also American football, where you have completion percentage over expectations. But there's many more of these kind of metrics out there. And they're nice, right? Because they're kind of intuitive and easily interpretable, but there are some issues, right? And to kind of motivate these issues, or to give you some idea of what I mean by issues, I will give you an example. And since I'm from Europe, we're going to talk about soccer, right? So I'm going to talk about goals above expectations, right, or GAGs. And to be a bit more formal, what we have is we have shot data, right? And you have an outcome for each shot. A binary outcome could be a goal or not. And then for the shot data, you can estimate a model, right? So what you would do is you would, in some sense, estimate this conditional expectation of y given z, and z are some shot-specific features, right? So it's typical features that you would use for an expected goals models, such as distances, angles, and so on, right? And then you basically look at a player, look at all of his shots, and you compare the actual outcome to the expected outcome. So in essence, you count the number of goals and you subtract the number of expected goals from all of his shots. And if it's positive, then it's good, right? We can interpret this as an overperformance. The player somehow, was better than expected in some sense. And if it's negative, it's bad, right? So this is kind of nice to interpret and nice to analyze, but there are problems, and this has been kind of discussed in the literature, right? There has been some issues that have been raised. So, for example, people say that it's unstable and it has limited replicability. So that means basically GAGs from one season is poorly predictive of the GAGs in the next season. And this is typically not something we would want from a metric. We have a problem of sample size, right? Shots simply are rare. You only observe so many shots. and this may lead to high uncertainty, and it's kind of difficult to quantify this uncertainty in some sense, okay? And then you have biases arising from data. So what we mean here basically is if you think about shot data from one season, what you actually see in the data is more shots from top players and top teams because they simply create more chances, right? Okay, and you can have a similar thing if you're interested in a specific type of shot, for example, headers or footers or long distance shot and short distance shots. So depending on how you train your model, you may introduce some biases in there, right? And so all of these kind of criticism have led to GAGs being labeled a poor measure somehow for evaluating shooting skills. And while I did enjoy reading all of these papers and kind of they raised important points, I still was not convinced that this is kind of the final answer to here. And there was kind of this question in my head nagging me of whether GAGs really is a poor metric for evaluating players. Okay, and so obviously, I then took a look at it myself, and I want to take you through our thought process in some sense. So we made some nice or interesting connections with classical statistical modeling, and then we tried to extend it in some sense. And I will talk about it from the perspective of GAGs, obviously, but you can think of, I mean, in the back of your head, you should have that this is basically all of what I tell you is applicable from for any kind of expected value metrics in the sport that you may be interested in, right? Okay. So, what we started with was shot data, right? We want to identify outstanding shooters. And the general setup that we have is, again, we have shots, we have a binary outcome, it can be a goal or no goal, and then we have a range of shot-specific variables, right? The classical variables that you would use that may help in predicting the outcome. And then, since we're interested in evaluating players, what we actually need is some measure for one player of shooting skill, right? So what we do is we add, we take one player of interest, we add one variable there, it's a binary variable, whether the player was the shooter or not, okay? And then if we want to somehow identify whether he's a good shooter or not, what we could do in classical statistics, we just use a logistic regression model, okay? So we model the log odds of the probability of scoring a goal as a linear function in our variables x and z here. Okay, and particularly we're interested in x, right? So we're interested in this parameter beta. It's also nicely interpretable in this model, right? It's just the effect the player has on the log odds of scoring, on the probability of scoring in some sense. And the nice thing is you can do inference on beta, right? This is well understood for decades. We have all these kind of nice tests which are all asymptotically equivalent. It's cool. So I want to talk about one specific test here, namely the score test. So this is was developed by Rao back in the 1950s, I believe, or even earlier. So it's out there already quite a long. And what it looks at, or what it targets, is the score of beta. So this is defined as the partial derivative of the log likelihood with respect to beta. And if you're in this logistic regression model, it's actually not all too difficult to kind of do the math and see how it looks like. So basically, you get this formula here, where you again have your outcome here. You have here some estimate for your probability of scoring in your logistic regression model. So you can think about this basically as an expected goals model, where you use a logistic regression under the H null, right? So you somehow exclude the variable x in your data. And now if you look at it, and if you recall how I defined GAGs, you basically see it looks very similar, right? This first part, you have these differences here. You multiply here with an x, but in essence you sum here over n, so over all of the shots, here only over the shots of the players, right? Now, since x is binary, right, it's only one when the player of interest was the shooter. Actually, all of the other terms vanish here in the sum, so actually what stays over is really GAGs, okay? So this is nice, right? Basically, what you see is that GAGs, in some sense, from a statistical perspective, is quite intuitive. And the nice thing is you can get uncertainty quantification in some sense, right? So we know the theoretical asymptotic distribution of your GAGs, and you can get confidence intervals and p-values. And plus, you can actually interpret it differently, right? You can interpret GAGs now as a player effect on the log odds of scoring, okay? So this is very nice, but obviously the problem is this kind of strong modeling assumptions, right? We would not generally believe that this kind of linear model relationship hold, and Also, this is kind of what the literature shows us, right? If you look at XG models in literature, then all of the people, they use basically fancy machine learning models, okay? But the problem is, if you use that now, you somehow lose all of this nice uncertainty quantification and interpretation, okay? So the question is, can we do better, right? Can we use machine learning models but still somehow get uncertainty quantification? Okay, and to do so, we extend this classical logistic regression model very naturally, right? So what we look at is the partially linear logistic regression model. So it's very similar, right? You still model the log odds of the probability of scoring as a linear function in your x variable, but you're a bit more flexible for the other variables, okay? So in essence, this is nice because the interpretation of your player effect is the same, right? You can still interpret it as before, but under the H null, actually, where beta is 0, you're actually completely model agnostic about the relationship between Z and your outcome, okay? So you can try to learn this from the data with some kind of machine learning model, okay? So for player evaluation, we're again interested in inference on beta. Right, so we want to do that, and you can actually do that using a non-parametric condition independence test, the GCM test, or generalized covariance measure test. And I don't want to go into the details here, but there's a direct connection between beta and the GCM test, and so on. So the details are a bit technical, so you can read them up in our paper if you want to. But what I will say, though, is that what you look at for this generalized covariance measure test is the generalized covariance measure, which is defined as the expected conditional covariance of y and x given z. Okay, so if you want to do the test, if you want to do inference on beta, what you actually need is an empirical version of that, right? So you need to fit, in essence, two models. One here for the outcome, which in essence corresponds to your HG model. You can use now as a machine learning model. And you need a second model here where you somehow model the propensity of a player taking part into a shot or taking a shot in some sense. Okay, and we call this residualized version of GACS because you see it's very similar, right? The first part is actually the same, but instead of multiplying here with a binary variable, you multiply with this residual here, okay? And so to contrast to GACS, so what we have is, as I said, GACS in a parametric model. It's kind of nice because you get this valid inference, but only if your linear model assumptions hold in some sense, okay? As soon as you go away from that and use machine learning models, you somehow lose this ability of doing valid inference, okay? So if you look at rGACS now, here the nice thing is you can use machine learning models to fit both of these regressions that you need. You still get valid inference. You still get the interpretation as a play effect in a partially linear model. And actually, from a domain-specific viewpoint, you can even somehow, so you can even interpret this kind of additional regression that you have to do, because what we're doing is actually we're modeling the propensity of a player taking a shot. So we're acknowledging the fact that somehow different players have different shooting profiles, right? A good player may take a shot that a weak player is not even thinking about, right? Or something like that. Okay, so what we say is that you should actually use rGACS instead of GACS. So the nice thing is if you're used to GACS, if you used it, rGACS is not very different, right? It lives on the same scale. This is somehow nice, so you don't have to get used to a new value that you somehow have to interpret. You can use your XG model that you like. So if you have the best XG model out there, you can still use it for rGACS the same as for GACS. But now for rGACS, you get somehow valid uncertainty quantification, even when you use a machine learning model as your XG model. You get different interpretation, right? So you can have kind of this different view on what you're actually looking at. And actually, rGACS addresses some existing issues that you have, but I will get to that in detail in the applications. Okay, and then, as I said, the nice thing, the whole framework generalizes very straightforward to any type of expected value metrics, right? And most importantly, your y does not need to be binary. Okay, it can be basically anything in some sense. So that's very cool. So you can use it in different sports, and it may be useful for other use cases. Okay. And another nice thing is that you can actually do all of this very nicely in R with the comments package of my co-author, Lucas. Okay? Okay, so now maybe to the most Yeah, interesting part, the applications. So we'll start with obviously evaluating shooting skill in soccer. So we start with GAGs. We have event stream data from Hudl StatsBomb from the top 5 European leagues of the 2015-16 season. So it's sadly not very recent, but it's the best openly available data set that we have. We do the whole procedure, right? So we extract basically the most common shot-specific features. We add one feature that's not very common, namely a team strength feature, which we believe is important, or which we found out that it was important, but I have not really time to talk about it. We use, as XG model, we use an XGBoost model, also quite common choice, and then we also need something for the X regression there, we use random forest, okay? And these are the results now, okay? So on the left side, what you see is the comparison between GAGs values and rGAGs values, okay? And probably the most striking result is that they actually look quite similar, right? So there's a high correlation. They actually live on the same scale, right? This solid black line is actually the identity. So in some sense, this is nice because rGAGs does not really do something different. But now what you can actually get is kind of these green dots here. And they somehow tell you which player significantly outperformed in terms of rGAGs, right? So, or you can interpret it now differently. You can, it tells you which player had a significant effect on the log likelihood of scoring a goal from a shot, okay? And for each player, you can rank them, obviously. You can get now confidence intervals, which is very nice, right? So looking at the plot, still, I believe there's kind of this question whether rGAGs really is better. I mean, you can get uncertainty quantification, that is nice, but I mean, you see they basically do the same, right? And we had this kind of criticism of GAGs, right? So let's just recall it a bit. We had this kind of problem of instability and limited replicability, right? So what you would in general then do is kind of look at rGAGs and GAGs values over season, see if something is more stable, but obviously since there's no data, I could not do that, but let me just tell you that we can have at least one advantage now with rGAGs because we can kind of think of different notions of stability, right? Because instead of just comparing the rGAGs value over seasons, we can compare p-values over season or something like that, right? We can compare significances, okay? The other thing is the low effective sample size and hence the high uncertainty. Well, I mean, the low effective sample size is not really solvable. This is just innate to soccer, so there's no real methodological remedy for that. But the nice thing, as I already mentioned quite often, is we have now valid uncertainty quantification in some sense, so we can at least get a feeling of this high uncertainty, okay? Then there's biases arising from the data. Okay, and this is probably one of the most important points. And what we actually believe is that rGAGs helps in this case, right? So it reduces bias because we actually are modeling this addition. So we have this additional regression where we model additionally the propensity of a player taking a shot. Okay, so this is kind of, the belief is not very irrational. It comes from statistical theory, right? This is based on this biased machine learning literature where we also took ideas from. And to show you how this looks like, I have another, I did another exercise, so we want to look at now how GAGs and rGAGs are affected by data selection. Okay, so what we have from Hudl StatsBomb is actually a full biography of Messi matches and shots from these matches when he was at FC Barcelona. And so what we do now is we fit 3 different XG models. One model basically trained on all of the data, where you now have a huge overrepresentation of FC Barcelona and Messi shots, so you believe that this is kind of very biased towards high-quality shooters, right? FC Barcelona is a very good team, Messi is a very good player. We use another model, which is basically the same as before, of the top 5 European leagues. Here, we still believe there's a bit of overrepresentation of top players, right? Because they shoot more, but we hope it's a bit more balanced. And then we train a model on shots from players that take less than 30 shots in the data. And since we believe that good shooters, they shoot more often, we believe that this low-frequency shooter model is somehow representing low-quality shooters. Okay, and then we want to look at how GAGs and rGAGs are affected by the choice, right? And these are the results for some of the players in the data set. Okay, so first of all, what you see, Messi actually very good. He outperforms all of his other players, but we also have like a very big overrepresentation of Messi shots, right? But what's maybe more interesting is looking at GACS and argx values. So the argx values are the dots, and the GACS values are the crosses. And what you see is that the discrepancy between GACS values, when you use another model for your XG, when you use a different XG model, is actually quite large, right? So you see there's a large difference between GACS values using different models, and when you go to argx, actually you see they're much closer together, okay? Here there's still slight a bit difference, but it's much closer, and you see this basically for all of the players, right? The GACS values, they are just more affected by what kind of model you use, and the argx values are less affected. Okay, so this is another plot just to mention this idea. So basically, on the left-hand side, you compare argx values between models. On the right-hand side, you do the same for GACS values. And what you would hope is that actually all of these dots lie on this black solid line, so the identity. That would mean your values are not very affected by the choice of model that you use. And you see for argx, they're actually much closer to this solid line, whereas for GACS, there's a higher discrepancy, meaning that GACS is much more affected by the choice of data, or by the data that you have for your XG model, okay? So this is very nice. I don't know how much time do I have left? Okay, very good. So I have other examples. So for example, I have basketball. You can do something else for quantified shooter impact here. Basically, you can do the full analog of what we did for GACS, if you just fit the model to the binary outcome data of whether a shot ended in a goal or not, right? So you can do this. Again, we propose to just use a residualized version, and we have a small example of 2022-23 season, right? And you basically see similar things. So the metrics are not too different, but you get this valid uncertainty quantification. You can interpret it from a domain-specific perspective if you want to. I think it somehow makes sense, right? But basketball is a bit more specific because actually you have a distinction between 2 and 3 pointers, right? So in essence, just modeling whether the outcome was so whether you scored a field goal or not, somehow ignores that there's actually 2 pointers and 3 pointers. So now actually what you could do is you can just fit the model for 2 and 3 pointers separately and then analyze the whole thing. But actually, the nice thing is that you can do all of the things with also a different outcome. So you can use a scaled version of that, or you can simply use the score directly. And you can do the whole thing, the same thing. You still get some valid uncertainty quantification. You still get results which are kind of similar. You get this kind of, nice uncertainty quantification, and so on and so forth, okay? So this is very cool. I also have an example for American football for completion over expectation, which also is basically the same, right? I'm not going to go too much into detail. And so let me quickly conclude, right? So what I told you is that, so we looked at the expected values metrics, right? So where you compare an actual outcome to an expected outcome. And if you use a parametric model for modeling your expected outcome, you can actually draw a direct connection to a score statistic, which is nice because it kind of gives you a different interpretation, right? And you get some valid uncertainty quantification. But the problem is you only get that in this strong generalized linear model regime, and you cannot use machine learning models. So that's why we propose to use a residualized version of this, where you actually get valid uncertainty quantification. Even if you want to do fancy machine learning model, you're very flexible in the choice of machine learning model that you deem reasonable. You still have the interpretation in this partially linear model, right, for your model parameter, and actually it addresses some existing problems with this expected value metrics. And we use kind of modern statistical tools such as double machine learning and non-parametric conditional independence test, right? And before I stop, actually, so we're working on, you can actually also do this for other types of metrics, right? So there's this kind of added value metric. So what you would do is you would kind of get a value function for a game state, and you would compare it basically to the So you compare the value before an action, after an action, and you would attribute this difference to a player, right? And you see there's a lot of examples, right? In soccer we have a number of these because soccer is very low scoring, but in American football you also have expected points added, okay? And you see, actually, for example, of expected points added, it's quite similar. The outline, right? If you look at expected points added, if you write it down in a bit weird way, then you see it looks quite similar to the metrics that we looked at. There's a bit of differences. You have to be a bit careful, but in essence, what we propose is to use a residualized version of that. And actually, for this case, you actually also have to model somehow your new outcome, which is basically the value at the after the action. Okay, and you have to be a bit careful about the assumptions that you do, but still you can get valid uncertainty quantification. You have to be a bit careful because you need to fit more models, so you need to be careful about data bleed. But in essence, you somehow get something similar. It's not so close together here, so the picture is not that nice anymore because EPA and rEPA are actually a bit different. But yeah, that's just what I wanted to give you on your way. And so thank you very much. Don't forget to scan the QR code, and yeah, I'm happy to take questions.
Okay, time for a question. Yes, in the middle here. Yep.
So you're assuming some level of independence between observations, but in soccer, I'm not quite sure if that's a valid assumption.
Yes.
As, like, for example, off of a rebound or a goalkeeper deflects it and then you have an easier shot or things like that.
Yes.
So I don't know if independence is, can you comment on that assumption?
That's a very, very good question, a very good point. So in some sense, you're right? So in soccer, you have to be careful. I think for shots, it's, well, I mean, obviously you have kind of, you have a problem with deflected shots and rebounds and something like that. But in some sense, well, it's at least the most fair to do it with shots, but the other thing is, so what we assume is some kind of conditional independence, right? So if you somehow capture all of what you think that doesn't make it independent in your Z variables, then actually you can somehow omit it. But I agree it's very tricky, so you have to be a bit careful with soccer shots, for example, with rebounds or something like that. It's a good point.
All right, one more question behind you, Mark.
Oh, wow, look at this. So first I'll start with a comment and then a question. The comment is, I'd love to see expectation gotten rid of, maybe take a page out of baseball and do above replacement. That might be a better way to think about it, right? And you're kind of getting that with getting rid of the good players. So that's the comment. The question is, do you think about multiple comparisons? And one of the advantages you have is you get valid inference. So are any of the soccer players better than, the null value average when you try to adjust for multiple comparisons and post-selection inference? Or is only Messi the only one who's actually good?
Well, I mean, there's certain things that you have to take care, right, or that you have to think about. I mean, it's not only, in this example, Messi, actually, we had a lot of Messi shots, and also we're only measuring shots, right? Because soccer players, they probably have different things to do also than only shooting, right? And in this case of Gags, it only works for that. But
Very close to zero.
yeah, but
Very top ones. You see a few by chance. So.
Yeah. Maybe that's true. I mean, there's so if you where are the results? Okay, if you have that, I mean, it's kind of tricky, right? And shooting is difficult, evaluating is difficult. I mean, I think it still depends on a bit on the sample size that you have, but. I mean, you still see differences, right? You still see some significant players, and you also, on the other line, you would see some other players that were not significant. So you can somehow distinguish, but it's tricky. Yeah, I agree. I mean.
All right, one last question we had here. No? Yep. Yeah, right beside you, Mark.
Well, on this plot, is this interval, is that confidence interval?
Sorry?
Is this confidence intervals?
Yes, so this is confidence interval for the Ajax value when you use the all data model.
So the coverage, so this will be say 95% coverage?
95%, yes.
And this is, so in your uncertainty metrics, it looks like your uncertainty metrics is a summation, right?
Yeah.
Can you go to that?
So, I mean, You basically mean this,
Right.
this thing, right?
Right. And this, don't you need to average this?
No, actually averaging, I mean,
I mean,
so-
uncertainty, you have an uncertainty.
So you have to standardize it. Yes, that's true. I mean, that's somewhat true. You have to take into account all of your shots that you have in the data. But you don't need to average it for only the shots of the player or something like that. Because this is also a random number, right? So this would not, this would actually add more uncertainty in there. But you need to standardize it in some way, that's true, yeah.
All right, I think we'll move on to the next talk, but let's thank Robert again.